All right, people, this is lecture on vertical circles, and many of the vertical circle problems are roller coasters, where you can see the circle is like kind of a frisbee in a vertical plane as opposed to, the way you throw a frisbee in a horizontal plane. All right, so that's what we mean. And we're going to learn some new vocabulary. So what do you think your true weight is? Okay, so we just called it weight before because we weren't distinguishing it from what we're going to call apparent weight. But your true weight is your attraction to the earth below it. And there's a formula for it. It's equal to mg. Okay, quick review question. Do scales measure weight? And the correct answer is no. Weight is an interaction between the potatoes and the earth. What the scale measures is how much, this column is squished. It's squishing something inside, compressing a spring or something. It basically measures the normal force. All right, so your nervous system can't measure weight because that's between you and the earth. So apparent weight is just a fancy, fancy word for the normal force. That's what you appear to weigh, right? Because I could put my hand down on this scale and I could make the potatoes appear to weigh more, or I could lift them up a little bit and I could make them appear to weigh less. All right, so what do you think apparently weightless means? Right, it means that you appear to have no weight. So what that means is that the normal force is 0. So when this person is jumping in the air, just like when, if I told you the story this year, me and all my friends, future friends, stuck in the elevator. When we were in the air and we jumped, we were not pressing on the elevator floor. If there were a scale right here, we would not be pressing on the scale, and the normal reading on that scale would be 0. So we appear to be weightless, even though the earth is absolutely pulling us back down towards earth. That's why it's called apparent. We're not really weightless, we just appear to be weightless. All right, so there is 3 classic positions on the roller coaster. So the good news is there's no vector breakdown for these problems. The other good news is there's going to be 2 forces. There's always going to be the normal. There's always going to be the weight. But you need to be careful about when the normal is more than the weight, when the normal is less than the weight, positive and negative. Okay? So, okay, so first thing I want to talk about is it doesn't look like there's a circle here, but if you imagine taking that section of the track, and if you know like the little wooden train tracks you can get for Thomas the Tank Engine, if you took that slice of the track and got a whole bunch of wooden train track pieces with that shape of the function and put them together, it would form a circle of a certain radius. Okay, that's called the degree of curvature of the function. There's a sophisticated formula for it, but that's what we're talking about, even though it doesn't look like a circle. At that point right there, instantaneously, there is a circle. And so this is a pretty tight circle. You can see this section of the track would make a much bigger Thomas the Tank Engine circle. So this has a lower degree of curvature. Kind of like back when we were looking at the parabolas, and this would be, an extreme acceleration and a less extreme acceleration. Okay, so position number 1 on the coaster is the coaster is right side up and is at the peak. Okay, so the first question is it possible for the coaster to lose contact with the track at this point? All right, and the answer is yes. If it goes too quickly, you can think about inertia. The coaster wants to keep going in this direction. What's making it turn is the force of gravity. And remember the hover disc demo, if you don't push inward with enough force, you're going to fly off tangent. So yes, it is possible to lose contact, which means the normal goes to 0. So next we're going to do the math to show you why that's true. Okay, so at the top of the coaster, here's your object, your coaster car. And remember, the new rules are any force pointing towards the center of the circle is positive, and any force pointing radially outward is negative. Okay, so the rule is in must win. All right, so still the same checklist for forces. Yes, it has weight. I'm going to call that W. And it is touching a surface, and surface is push. So there's a normal force. This looks an awful lot like a boring problem. But if it were a boring problem, it would fly off at a constant speed because the forces were balanced, and it's not. It's turning. So in must win. So the weight has got to be bigger than the normal. Okay, so then we're going to apply our circular motion equation, which says that the force of the weight, which is pointing in, minus the force of the normal, because it's radially outward, equals mv squared over r. Okay, remember, you can never feel your weight. That's between you and the earth. I'm going to subtract force of the weight from both sides. And then I'm going to multiply by -1. So your normal force, which is what you feel, so I'm going to distribute, multiply everything by -1. So that becomes positive. This becomes negative. This becomes positive. So to clean that up, this is what you feel. That's your normal force or your apparent weight. And it's equal to your true weight minus stuff, right? And this stuff is always going to be positive because m is positive, v squared is going to be positive, r is positive. So don't memorize this. I want you to be able to derive it and see why it makes sense. But at the top of the coaster, your normal is always going to be less than your weight, which should make sense logically. I don't want you to just memorize it, because your inertia is literally carrying you off the track, which is going to reduce the normal force, potentially to 0. Okay, and that's why your stomach kind of feels funny at the top, because the stuff inside your stomach isn't pressing into your, stomach lining as much as you usually is. Okay, that is position number 1. Position number 2 on the coaster is at the bottom when you are instantaneously going in a circle like this. So that's the center of your circle. So is it possible for the coaster to lose contact here? And the answer to that is no. Again, all of these have to do with inertia. So what does a coaster want to do? It wants to keep going in a straight line. So it is literally slamming itself into the track. And the track's job is to say, no, I don't want you to keep going straight. I want to force you to turn. Okay, so we're going to look at the force diagram for this location. Center of the circle is positive. Radially outward is negative. So again, we have weight pointing to the center of the earth. Oops. That's a good trick. And the track electron clouds are being squished really hard, right? Because that coaster is just heading right into them. So we have the force of the normal. Okay, and then we have sum of the forces equals mv squared over r. In must win, so we have the normal in and the weight radially outward equals mv squared over r. We want to know what you're going to feel, right? So we want to solve that for force of the normal. So we're going to add Fw to both sides. And then, again, this should make sense. The normal force is your true weight plus stuff that's always going to be positive. So at position number 2, your normal is guaranteed to be greater than the weight 100% of the time because it's equal to the weight plus extra stuff. And that's because the normal force has 2 jobs. I got to support the coaster and I got to turn. So I need extra force to push it inward in order to keep it from flying off tangent. Okay, final location on a roller coaster, and then we'll do an example problem. Final location is position number 3, which is upside down in a loop-de-loop. So, is it possible for the coaster to lose contact with the track at position number 3? Okay, hopefully that makes sense. That yes, it is possible, because clearly if I just put the coaster there, it was 0 speed, it would fall down, right? It would lose contact. So, but it is also possible to not lose contact, which seems weird. So I'm going to do the bucket of water demo in real life. But again, think about inertia. This car is, if it's going counterclockwise, is trying to fly off tangent. So it is literally, again, slamming itself into the track. Now, gravity is always there. You can't make it lesser or greater. That's a set number. So if I'm not going fast enough, then gravity is more than what it needs. Like I'm pushing that hover disk too hard. It's more than what it needs to turn, and it's going to overturn and go in a smaller circle, which means it's falling out. Right? So what I need to do is go fast enough that I need it more than the weight, like that I'm going so fast, the hover disk is going so fast around that circle, that painter's tape in the lab, that the weight itself is not enough to turn it. And so I need the electron collect. I'm going to slam myself into the track, and I need the weight and the normal in order to turn successfully. Right? So hopefully that makes sense logically, and then we'll prove it in a minute. All right, so final location. Coaster upside down. Here's the circle. Center is positive. Radially outward is negative. It has weight pointing towards the center of the Earth. The track electrons can only push. They can't pull in. So we have the weight and the normal, and they're both radially inward, which is okay. In must win, but it doesn't have to be fighting something. It just means that there needs to be more in than out. Okay, and so we have sum of the forces equals mv squared over r. We have the normal force and the weight, and they are both potentially, right, if the normal isn't 0, they're both potentially helping it go in a circle. Okay, we want to know what the pressure is with the track. We want to know what the normal is. So this is the trickiest logic, because so the force of the normal, if you remember the other 2 examples, you started with the weight. That was your reference, and then you added or subtracted the mv squared over r. Here you start with the mv squared over r, and you're subtracting the weight. Okay, so this normal could be more than the weight, right? If all of this stuff together, let's say the weight is 60 newtons, or 600 is more like 600 newtons for a person. That's fixed, right? That's the weight, true weight. You can make this whatever you want by making V really big or R really small. So let's say all of this junk together is 1600. Okay, so the true weight is 600. The normal force is 1600 minus 600. The normal force is 1000. Right? So I feel heavier. Or let's say, again, the true weight is 600. Let's say that R, like V, is really low. And so this happens to be, well, it could be 600, right? So the normal force could be 0 if I have the exact right combination of speed and turning radius. But it could also be, let's say that this is 800 newtons. Okay, then my true weight 600, my normal force is 800 minus 600, so then the normal is 200, which is less than the weight. So I feel lighter than normal. Okay, and then just to make sure we can do the problems, I'll make the problem a separate play pause because I'm at 15 minutes. If the problem says, kind of like static friction, find the minimum or maximum speed you need to go, that means the normal force is 0. And I either need to go faster than that to make sure that I don't fly off, or in this case, slower than that so I don't inertia myself off. Okay, so again, in these problems, max and min, to not lose contact or not fly off, just means set the normal equal to 0 and then use logic to decide whether that's a maximum or a minimum. Doesn't mean do calculus. All right, that is vertical circle big picture note, and then we'll do an example problem in another video. Thanks for listening.